Hello, Luke. Welcome to lesson 74. So today we're going to be talking about scientific notation. And it's pretty straightforward, so hopefully we can get through it fairly quickly. But the basic idea is sometimes in science we deal with very large numbers, or on the other hand, very small numbers. And you trying to compute different problems using such small or large numbers can be really cumbersome and sometimes just almost impossible. All right, because the numbers are so large, it's so easy to make a mistake, and it's just very, very cumbersome. So, for an example, just to illustrate my point here, let's just say that we were trying to decide how many atoms were in a drop of water. All right, so that's my question. How many atoms? Here is a very large atom on the screen, but how many atoms are in one small droplet of water? Okay, and you might guess that this number is going to be quite large. There are probably a lot of atoms in a single drop of water. And actually, you would be right. There are many, many, many atoms in a small droplet of water. Now, this kind of depends upon the size of the atom and the size of the drop. But just for some perspective here, we'll give an estimate, and we're going to say that there are about, let's see, 501 followed by 19 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. All right, so there is our number. This massive number right here. That is approximately how many atoms would be in a droplet of water. All right, you can see it's a huge number. Now imagine what we'd be doing if I were to say, oh, great. Well, then how many atoms are in, maybe 1,268 drops of water? Okay, so what happens if I have 1,268 of these? Well, now I have to multiply this big nasty number by 1,268. And even 1,268 is not a very large amount of water. Okay, so you can see how these numbers become quite cumbersome because this original number is so large. All right, here's another example. Let's switch it up. Let's take that atom from the drop of water, and now let's try to measure it. Okay, now this is obviously not to scale. It's just to kind of give you an idea of what we're doing. We're trying to take a ruler and just kind of measure the size of an atom. Okay, and you might guess that in this case, the number is really, really, really small. Okay, an atom is very, very tiny. So what's the measurement of an atom in, well, let's say we're asking in meters, for example. What would the measurement be? How many meters are in an atom? Well, the answer would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to go conservatively and say 3. Atoms change, or they're different in size depending upon the atom that you're looking at. So this would be kind of a nice middle number. So you can see that this is very, very, very small. Okay. So again, we have two numbers here that we've looked at. One that's extremely large and one that's very small. Okay. And in science, we're dealing with numbers like this all the time. All right, so scientists got tired of trying to write these very large numbers and very small numbers and then using math to multiply or divide or do whatever it was that they were trying to do in their equations. All right, so they developed another way to look at these very large or very small numbers, and that way is called scientific notation, which is what we will be looking at today. All right, it's just a way of writing very, very large numbers. Okay, so how do we do it? Well, let's talk about it. Let's just take, for starters, let's just take the number that's not too large. Let's say we've got 6,262. Well, yeah, let's take that, but then we're going to add maybe 6 zeros to the end of this. Okay. Now, here's the thing. In science, many of these numbers that we're dealing with, as you could see even in these last two examples, they deal with a lot of zeros, okay? Most of the time, the very large numbers are going to have a ton of zeros after a certain number of integers. And then same thing with the very small numbers. We often have a decimal point followed by a bunch of zeros and then some other integers after that. Okay, so it seems that there are just a lot of zeros in these large numbers. So what scientists decided to do was to use the rule that we've talked about many times now, and that is kind of the 10 rule. If I have a number such as 62, and I'm going to multiply that by a 10, what happens here? All we do is add a zero, right? So it becomes 620. And I can do this with anything. I can take 37, it's 37,462, and I can multiply this by a 10, and all I have to do is add a 0 to the original number, 4620, and that is my new number after I've multiplied it by 10. All right? The same thing can apply with decimals. All we're doing is moving the decimal point over one place. When I multiply something by a 10, there's that invisible decimal point right here. And all I'm doing is moving it over to the right, one location, which means that that location has to fill up with a 0, and we get this 620, and now the decimal is here, right? It was right after the 2. We've moved it one position over, and that gives us the 620. Same thing applies here. I had the 37,462. The decimal was right here. I simply moved it over one location and set it right here, and that gave me the new number. So when we multiply something by 10, all we're doing is moving the decimal place one position to the right. Okay? So that would work too if I have a decimal. So if I have the number, 32.75, and I'm going to multiply this by 10, what happens? Well, the same rule applies. We're simply taking that decimal point and we're moving it over one location. Okay, so it becomes 327.5. Do you see how I moved that decimal over one location? All right, that's all that we do when we're multiplying numbers by 10. All right, so the cool thing is, what happens if we start to give us powers of 10? So if I have, 12.68, and I multiply that by a 10, well, we know how to do that now. But what happens if this 10 is, say, to the second power? Okay, well, what does that mean? Well, that means I'm taking 12.68, and I'm multiplying it by a 10, and then multiplying it by a 10 again, right? I'm multiplying it by 10 twice. 10 times 10, 10 squared. So if I think of it that way, the first 10 is going to make this decimal point, maybe I'll go in a different color here. It's going to make this decimal point move one position over to the right and puts it between the 6 and the 8. But then I multiply it by this second 10, which is then going to move that decimal place over one more place to the right and puts it right here. So my answer is simply 1268. I moved the decimal over twice. Okay? Hopefully you see how that works. The same thing would apply if this were 10 to the third. If it were 10 to the third, well, then I would move it yet one more position over, and I'd have to add a 0. Okay? So, knowing that, all that we need to recognize is that if I have a number and I'm multiplying it by a 10 to some power, let's say it's 10 to the fourth, this power indicates how many positions I need to move the decimal point. So in this case, I need to move the decimal point 4 times. So it's going to be, once, twice, 3 times, 4 times. It's going to be right here, but now I have to add 2 zeros in here, right? So the answer is 374 followed by 2 zeros. Okay? Do you see how that works? So again, just to recap that, the exponent, when we multiply something by 10 to an exponent, the exponent is going to tell us how many places to the right we are going to move the decimal point. Okay? Now, the same thing applies for when we divide by 10. So if I have something like 370 and I'm dividing it by 10, okay, what happens then? If I divide it by 10, that means that I move the decimal point not to the right. Over here I moved things to the right. I move the decimal point to the right. Here, when I'm dividing, I move the decimal point to the left. Okay, so I have my decimal point here originally, but now after I divide it by 10, I'm going to move it one position to the left. And I end up with 37.0, which is equivalent to just 37. Okay, and that should make sense. 370 divided by 10 is 37. Okay, now a way to put this in maybe a little bit more of an algebraic form, we could say 370 times 1/10, right? Is that not the same thing as taking 370, dividing it by 10, which is what we did up here, right? 370 times 1/10. But now we could even take that one step further, and we could say, well, let's take this 10 in the denominator and let's move it into the numerator. We can do that algebraically by changing the exponent sign, if you recall. So that would be the same thing as saying 370 times 10 to the negative 1, right? If you don't see that, maybe pause the video and study that for a second. Make sure you can see how I went from 1/10 to 10 to the negative 1. Okay? So 370 times 10 to the negative 1 would indicate that we need to move the decimal point one position over to the left. So we move it from here to here. Okay, and it becomes 37. All right, so we can look at this and say, well, in this case, the exponent, if it is a negative exponent, that indicates that we move the decimal point to the left, the corresponding number of places. All right, so there's some rules here that we're starting to see. Okay, if the 10 is being raised to a positive exponent, then we move that many positions to the right. If it's being raised to a negative exponent, we move that many positions to the left. Okay, those are both just kind of background information for what we're going to be learning today with scientific notation. These are the things that the scientists realized. Oh, I can see how this 10 to the negative power works. I can see how this 10 to the positive power works. Let's use what we know now to try to write this number without changing its value, but writing the number in an easier to understand way. Okay? And this is what they developed. So this is it. This is the scientific notation part right here. So how do we do scientific notation? Well, they decided that they would always start from the left and work their way to the right. And what we're looking for is the first digit that's not a 0. Okay? The first digit that's not a 0. So in this case, we start with the 6 and we just check to see if it's a 0. Well, it's not a 0. Okay, that's pretty clear. So what we are going to do is we're going to try to rewrite this number with a decimal point immediately after the first non-zero digit. All right, so 6 is the non-zero digit. So what we want this to turn into is 6 point. All right, that's what we want, 6 point, and then we follow that with all the other integers to 6, 2. But as soon as we hit this 0 right here, and we recognize that everything after it is also a 0, well, then writing these zeros would be a bit superfluous. There wouldn't be any reason for it, right? Because anytime you have zeros at the end of a decimal number, you can just drop the zeros. So we don't need to worry about writing all these zeros. We just write 6.262, which is a nice small number in comparison to our original number, but we can't change the value of this. Okay, so what the scientists do here is they multiply this, and they don't use the dot, by the way. We use the dot all the time in algebra, but in scientific notation, they don't. They use the old multiplication sign. Okay, so they're going to multiply this by a 10, and we need to figure out what the power of this 10 is going to be. That's the question, because we don't want to change the value of the number. We want to keep the value of the number, but we need a power right up here. So what power should go in this spot? We need to take 6.262 times 10 to some power, such that if we were to multiply this out, we would get back to our original number. Okay? So to do this, we need to count up the number of places that are present after the decimal point. So again, picture your decimal right here, and then count up the number of places. We have 1 place, 2, 3, 4, 5, 6, 7, 8, and 9. There are 9 places after this decimal. Okay? So because there are 9 places after this decimal, this exponent, and maybe just to give myself some room here, we'll get rid of this empty circle. This exponent is going to be a 9. Okay? Because there are 9 places followed by this 6, following the decimal point, at least following where we put the decimal point. Okay? Now, the thing to recognize here, though, is we need to ask ourselves, is this going to be a negative 9 or is this going to be a positive 9? Because that's going to tell us the direction that we need to go if we were to try to get back to the original number. All right, do we move this decimal point to the left to get back to the original number, or do we move it to the right to get back to the original number? And clearly, we'd have to move it to the right. We'd have to move it this direction, because in the original number, the decimal point is way over here. This is where the decimal point is in the original number, right? We put it over here, but the decimal is actually here. So we have to work our way backwards now. So if we were to go backwards, we'd have to move this decimal place 9 places to the right. So do we use positive exponents or do we use negative exponents when we're trying to move it to the right? Well, remember over here, we use positive exponents. Positive exponents will move us to the right. And since that's where we want to go, this is going to be 10 to the positive 9. All right, so this is scientific notation. This is how a scientist would write this number, 6.262 times 10 to the 9th. Okay, it's not complicated, but it does take a little practice to become familiar with it. All right, so let's try another number. Let's say I've got this number, 3. Okay, try to write this number in scientific notation. Go ahead and give it your best try, and then we'll do it together. All right, so once again, we start on the left-hand side, and we just decide where do we want the decimal point, right? So we look at the first number, we say, oh good, that one's not a 0. So we want the decimal point to be right after it. Maybe I'll do this in a different color. So we want the decimal point to be right here. It's right here, right? That's where we want it. So we're going to rewrite our number with that decimal point in the location we've chosen. So it's going to be 3.414. The rest are zeros, so we don't need to write them. And this is going to be multiplied by a 10 to some power. Okay? Now, which 10 is it going to be? In order to get it back to where it started, we would have to move this decimal point all the way over to here. That's where it is originally. So to get it from here to way over here, well, let's put it way over here, how many positions would we have to move it? Well, we'd have to move it once, twice, thrice, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times. So this is going to be 10 to the 12th. And again, it's a positive 12 because we would have to move this to the right. Okay, to move that to the right. So we'd be using positive exponents. Okay? Excellent. Let's try some more of these. All right, let's say I've got the number, and maybe I'll just pull one from the book here. Let's say I've got 0.000316. Okay, and I want you to write that in scientific notation. Well, this one's a little bit different than the other ones because here, if we're starting from the left and working our way to the right, we have the first digit is a 0. Well, that's not something that's not a 0. We're looking for something that's not a 0. So we move to the next digit. Nope. Next digit. Nope. Next digit. Yes. Okay, so where do we want the decimal point? We want to put the decimal point right here. That's where we want it. All right. Now, if I rewrite it with the decimal in the location we've chosen, these original first three zeros don't mean anything. We just have 3.16, right? Because 3.16 is unnecessary. That's like saying, I'm going to write 72. I'm going to write the number 72 as 00072. These zeros are not needed, right? They're not needed to write 72. They're not needed to write 3.16. Okay, so we have the 3.16 as, what we want. Now that's going to have to be multiplied by a 10 to some power. And we need to check ourselves and see, all right, well, this is where we placed the decimal. Where do we need to go to get it back? We need to move it, well, over to here. So we need to move it once, twice, 3 times, 4 times to the left. And since we would need to move it to the left, then we need to use the negative exponent. Okay, so it'd be 4 places to the left, so we'd have to use the negative exponent. So it's 3.16 times 10 to the negative 4th. Okay. All right. Another way to kind of think of this is you're going to use negative exponents if you're trying to get back to a smaller number. All right. Look at this number. This number is actually bigger than this whole number right here. All right, so we're kind of going from, our answer, what we want, from a larger number, trying to get back to a smaller number. And to do that, we have to use negative exponents. On the other hand, with these problems, we have, 6.262, and we're trying to get it back to this very large number. So we have kind of a relatively small number, and we're trying to get back to a really large number. Well, then we have to use a positive exponent. All right, so if you kind of have to think backwards, but if you're thinking backwards, if you have a small number that you're trying to get into a larger number, it makes sense to use a positive exponent. If you have a large number that you're trying to get back to a small number, then it makes sense to use a negative exponent. You need to go backwards. Okay, so hopefully that kind of helps you remember whether to use positive exponents or negative ones. All right, let's try another one. What about this one? What if I have, let's see, 0.000417, and I'm going to multiply this by 10 to the negative third. Okay, now this is a good one. Now, at first glance, you might say, well, wait a minute, that's already in scientific notation. Well, it's a little deceiving because it does look like it is in scientific notation, but it's not. It's not in scientific notation. Look at it for a minute. If you have to even pause the video and ponder upon it a little bit, why is this not in scientific notation? Can you tell me? Think about what we've learned. Why is this not in scientific notation? Well, the answer is the decimal is not where we would like it to be. Remember what we said earlier. Scientists like to have that decimal point after the first number that's not a 0 as you read the number from left to right. So looking at this number, we see that this decimal point is not after a non-zero digit. It's actually just at the very beginning. The scientists like to have it after the first non-zero digit. The first non-zero digit is the 4. So really, they would want this decimal point to be right here. Okay, that's where they would want it, not the beginning of the number like this. So we need to rewrite this with the decimal point in the proper location. So this is going to be 4.17. Now we're still going to multiply that by a 10 to some power. Okay, so kind of completely ignoring this section right here. We're not even going to pay attention to this section right now. We're just going to write this number in scientific notation. So if I have 4.17, and actually let me give myself a little more room here. 4.17 times a 10 raised to what power? Well, to decide that, we have to go back and look at where we placed the decimal and ask ourselves, how do we get back to where we started? Well, we'd have to get back to this position. And to do that, we'd have to move the decimal 4 places to the left. And since we're going left, we're going to use negative exponents. So it's going to be a -4, right? Now, once we've done that, now let's bring down this second piece of the puzzle, the times 10 to the -3rd. Let's bring him down and put him in here as well. Times 10 to the -3rd. Now, if I do that, I can treat these two 10s as kind of like terms, okay? Or similar terms. So like, if I have an x squared times an x to the 3rd, I can combine these, I can multiply these by adding the exponents, right? Because they're like variables. Okay, so x times x, we would just raise or add the exponents. 2 and 3 is 5, then we'd get x to the 5th. Same thing applies here. We're going to treat these 10s as if they were kind of variables, and then we'd recognize that we then can just add the exponents. We can add these two exponents together. So this is going to equal the 4.17 times a 10, but now we add the exponents. -4 and -3 is a -7. So this is the proper scientific notation for this number. Okay? Does that make sense? All right, let's practice some of these and make sure that you've got these. So here we go. I'm going to take a couple of them here. I'm just going to pull them right out from the book here. And I want you to just pause the video and go ahead and try to write these in scientific notation. 10 to the -7. And then I'll give you another one. Let's give you this one. Times 10 to the -3rd. And then maybe we'll do one more here. How about okay, so here are 4 problems. Why don't you pause the video, try each of these, and then we'll do them together. All right, so let's see how you did. The first one, pretty straightforward. Again, we need to first decide where we want the decimal point. So we would find the first digit that's not a 0, and that's going to be the 4. So we're going to want that decimal point right here. Keep in mind where it is. It is right now right here, okay? But we want it after the first digit. We want it right here. So we'll rewrite it now where we want it, 4.78. And then we need to multiply that by a 10 to what power? Well, to get it back to where we started, we'd have to move it 4 places to the right. To the right means the positive exponent, so it's going to be a +4. So that would be our answer. Okay, it also makes sense that we're using a positive exponent because we're taking a smaller number and trying to get back to a really large number. Okay, so we're using the positive exponent. So there we go. There's that one. Straightforward. Let's try this one now. Here again, it's the same number. We still want that decimal point right here. So we're going to rewrite it, 4.78. Okay, and we're going to multiply that by some 10. And actually, it's what we have over here. We want the decimal point was right here. So to get it back, we have to move 4 places to the right, which means we're going to use the positive exponent. But we still have now this times 10 to the -7 here that we need to tack on the end. So now we can rewrite this as 4.78 times 10. Now what's a 4 plus a -7? A -3. So that would be our answer. Okay? All right, how about this one? Well, we have Our decimal point is here. Is that where we would like it? And the answer is no, it's not after the first non-zero digit. So where's the first non-zero digit? We have a 0, 0, 0, 8 is the first non-zero digit. So this is where we want it. Okay, so we're going to write it as just 8 point, which is just 8, right? And we're going to multiply that by a 10. But now to get back to where we started, we need to move our placed decimal 4 places to the left, which means we're going to have to use a -4 in this case. And then we can bring down the rest of the problem, which is this times 10 to the -3. So times 10 to the -3, and we end up with 8 times 10 to the -7. All right? Excellent. Now let's try the last one here. So 123.68. Where do we want the decimal? They have it here. We would like it after the first non-zero digit. So as we read it from left to right, we have our 1. It's going to be right after the 1, right here. So we have 1.2368. That's the desired number. And we're going to multiply that by 10 to some power. Going back and looking at this, we need to decide which direction we'd have to go to get it back to where it started. Well, we placed it here. We would have to go 2 places to the right, right? Since we're going to the right, it's going to be a positive exponent. 2 places, it's going to be a positive 2. Now we bring down this times 10 to the -4, and we can combine the exponents for the 10, and we get times 10 to the -2. And that is our answer. Okay? Excellent. If you got any of those wrong, maybe just try them one more time on your own. Make sure that you can do them on your own, because essentially this is what they are going to ask you in the text. So if you struggled with these, maybe back the video up and just look at it again and make sure that you can do these correctly. All right? If you got them right, great. Then I'd say you're in pretty good shape. So we will stop here today, and we will pick up on this again in future lessons when we talk about how to multiply or divide numbers that are in scientific notation. All right. I will see you tomorrow.